Good morning, everybody. In this video, we are going to be focusing on using both regular elimination and substitution and Gaussian elimination for solving some story problems. Now, there's three main steps in these problems. The first is to define your variables. The second is to write your system of equations. And then the third step is to solve. And the important thing, both with defining your variables and solving, is to keep track of your units. We need to use units in the context of the story problem, and we also need to make sure that they make sense in how we're defining our variables and writing our system of equations. So folks, we're gonna go ahead and just start by reading through this problem. It says 20 pounds of rice and 10 pounds of potatoes cost $16.20. So this is kind of our first sentence and possibly equation in our system. And then 30 pounds of rice and 12 pounds of potatoes cost $23.04. Then it asks, how much will 10 pounds of rice and 50 pounds of potatoes cost? So if we were to write an equation, we'd probably look at that first statement and say, well, I've got 20 pounds of rice and 10 pounds of potatoes, and that costs $16.20. So it seems pretty legit. I've got X being rice and Y being potatoes, but this doesn't actually make sense with the context of our units. This would be pounds plus pounds equals money. So there's a slight issue there where we have to be careful how we go about defining our variables, because pounds plus pounds does not equal money. So we need to have X be something so that when I take 20 pounds times it, we end up with money. So how can I get pounds to cancel out and end up with money? We would need dollars per pound. Same with 10 pounds. What can we multiply it by? Dollars per pound. And I know that kind of looks like 1B, but that's LB. That's the abbreviation for pound. So the LBs cancel and the LBs cancel, and that would give me money plus money is money, or $16.20. So instead of saying that X is pounds of rice, it's actually the cost per pound of rice. Cost per pound of rice. And then Y is the cost per pound of potatoes. So I've got my first equation set up for my system. For the second equation, we're going to have 30 pounds times the cost per pound of rice plus 12 pounds times the cost per pound of potatoes, and that is equal to 23.04. So if I wanted to solve this system of two variables and two equations, we can either use regular substitution or regular elimination. Now, I'm just going to go ahead and say that for this problem, because I think you guys can use elimination on this just fine, we would get X equals 0.6 and Y equals 0.42. Now, what is wrong with this as a final answer when we go about using elimination to solve this? The problem is we need to have units for this. So X is cost per pound. So if I put a dollar sign here, what else should I probably have with this 0.6? We need that placeholder of 0 on the end so that it says 60 cents per pound. Same with 42 cents. Put a dollar sign in front of it, and that is per pound. Now, something that I sometimes see with this, $0.60 is equal to 60 cents, but it is not equal to 0.60 cents. This would be part of a penny, or 0.6 of a penny, whereas this says 60 cents, and this says 60 cents, or 0.6 of a dollar. So just be careful when you are labeling your units for those. Now, something else to be careful about with these story problems is answering the actual question. So when I set up this system of equations and identified my variables, like, yep, X is the cost per pound and Y is the cost per pound, the question is actually asking how much will 10 pounds of rice and 50 pounds of potatoes cost? So to actually answer this question, I would need to take 10 times that 0.6, and I would have to take 50 pounds of potatoes times its unit cost. So times the 0.42. And that, grabbing my calculator, that would give me a final answer of 10 times 0.6 plus 50 times 0.42, a total cost of, woohoo, a straight up $27. So notice I had to be very careful with my units in writing my equations to make sure that I didn't have pounds plus pounds equals dollars. I had to be careful with my units in defining my variables and how I wrote what my variables were equal to. And I also had to be careful about what the question was actually asking me to solve for. So folks, that's going to be a hugely important strategy for those of you taking the ACT, is to look at that final question and see, what is the problem actually want me to find? So folks, we're going to go ahead and jump into the next problem. It says a theater charges $8 for main floor seats and $5 for balcony seats. If all seats are sold, the ticket income is $4,200. So I'm underlining these all the same color because they're all in terms of money. In the next sentence, it says at one show, 25% of the main floor seats and 40% of the balcony seats were sold, and the ticket income was $1,200. So this second sentence, I see that there's a problem with my units. I've got percentage of seats, so seats plus seats equals money. So we're gonna have to be careful about how we define our variable and how that's gonna work in our equation setup. And then looking at the question part of this, how many seats are on the main floor and how many are in the balcony? So let's go ahead and start by trying to write that first equation. So I've got $8 per main floor seats. So seats times cost per seat would be cost, or money. Then $5, the cost times the cost per seat times seats. That would be equal to $4,200. So unit-wise, this is all good. It's all in terms of money. So what do my variables represent here? If I have money per seat times something to equal money, we would have to have that be times the seats to get that to cancel, so that we would get money on the top. So $5 per seat times the number of seats, that would leave me with money. So what does that tell me about X and Y? Their units are seats. So X is going to be the main floor seats. We'll say the number of main floor seats. And then Y will be the number of balcony seats. So now for my second equation, it says 25% of the main floor seats. So 25%, we change that into a working decimal to use it in our equation. So 0.25x, and I'm gonna leave some space here and you'll see why in a moment, plus 0.40, or just 0.4 times Y equals 1,200. Now, That $1,200 is in terms of money. That's how much ticket income they make from selling that amount of seats. But right now, thinking about my units, 25% of seats is just a number of seats. So how can I take the number of seats and change it into money? Well, if this is amount of seats, it's actually similar to my seats I have up here. I still need to multiply this by the cost per seat in order to get my unit to be money. So I'm going to go in and just throw that 8 with my variable. That's the cost per seat times the seats, which gives me 25% of a dollar amount, and then 40% of $5 per seat times the seats. That would also give me 40% of a dollar amount. So this is how I would set up my equations. That is how the units would work out. So this would be another 2-variable system of equations, which we could then use elimination or substitution to solve. So let's go ahead and move on to the next problem, where a theater, more tickets. A theater has tickets that are $6 for adults, $3.50 for students, $2.50 for children under 12 years old. A total of 278 tickets were sold for one showing with a total revenue of $1,300. If the number of adult tickets sold was 10 less than twice the number of student tickets, how many of each type of ticket were sold for this showing? So thinking about totals, thinking about variables, I'm going to go ahead and start with this first statement about money. We've got $6 per adult ticket, so maybe 6x. $3.50 for students. I'm just going to write that as 3.5y. And $2.50 for children, 2.5z. Now it says a total of 278 tickets were sold. Do I want to set this expression equal to 278? Well, this is in terms of money. This is in terms of tickets. So in order for me to have money times something equals tickets, I would need to have tickets per dollar as my x variable. And I'm thinking that the x and the y and the z are going to be more as amount of tickets, because it's asking me how many type of each ticket were sold for the showing. So instead of setting this equal to the 278, since this total revenue is in terms of money, I'm going to set this equal to 1,300. So if this is money times tickets, is it really just tickets? Well, this is actually $6 per ticket, where x is the number of tickets. So 6 is the price per ticket. My variable is tickets. Those cancel, and we are left with the dollars or the units of that 1,300. So this helps me define my x, y, and z variables. X is the number of adult tickets. Y is the number of student tickets. And then z is the children tickets. So notice that this is our first one on this page that has had 3 variables. So when I go to write my second equation, we need to somehow use this total of 278 tickets. Well, thinking about the unit there, what do we know about tickets? We know that the adult, the student, and the children has to total the 278 tickets sold. So x plus y plus z equals 278. Now, my last statement, or my last equation, that is going to be the number of adult tickets sold. So adult tickets sold is x. And they say that was 10 less than twice the number of student tickets. So twice the number of student tickets is 2y. And then 10 less than that would be minus 10. Now, folks, as I'm looking at this problem, we've got money, we've got tickets, And then we've got another equation about tickets. Now, since this is a 3-variable system, we would want to use Gaussian elimination to solve. Now, if we went to label these, equation number 1, equation number 2, and equation number 3, there's something not quite right about the setup of equation number 3. Normally for elimination, we want our variables to all stack up nicely. So before I start thinking about which variable am I going to cancel out when I add those equations together, this one needs to be in standard form first, which means we want all of our x, y's, and z's on the same side, just like they are in equation 2. Just like they are in the first equation. So how can I get my variables on one side and my constant on the other? We're going to subtract 2y. So then x minus 2y equals negative 10. So now I would be ready to solve. And take note, going back to what we were doing in one of the previous videos with the Gaussian elimination, since this equation doesn't have a z, it's like this is already my A equation, so that would prompt me to try to eliminate my Z variable first. So folks, this is going to help you in the homework packet with that yarn problem especially, and some of the other story problems. So be careful with your setup. Make sure that you define your variables in terms of units, and you write your answers in terms of units as well. So if you want, you can try at least setting up those 2 problems down at the bottom, but in the next video, we are going to move on to lesson C and start talking about matrices.